Welcome back. In our last class, we learned about hybridization, how atomic orbitals mix to form new hybrid orbitals. But knowing just hybridization isn't enough to fully understand why molecules behave the way they do. Today, we'll dive deeper into molecular orbital theory, or MOT for short. Sometimes, hybridization fails to explain certain properties of molecules, like why oxygen is paramagnetic, or why some bonds are shorter or longer than expected. That's where molecular orbital theory comes in. It gives us a more advanced, quantum-based explanation of chemical bonding. MOT says that atomic orbitals combine to form molecular orbitals that are spread across the entire molecule. These molecular orbitals can be of two types: bonding orbitals, which increase stability, and antibonding orbitals, which decrease stability. From MOT, we can calculate something called bond order using the formula bond order equal to number of electrons in bonding orbitals minus number of electrons in antibonding orbitals, divided by 2. This tells us the strength and stability of the bond. Example, let's take an example. For nitroe, the number of electrons in bonding orbitals is 8, and in antibonding orbitals is 2. So bond order equal to 8 minus 2 divided by 2 equal to 3. That means nitrogen has a triple bond, which is why nitrogen is so strong and hard to break. MOT also helps us find whether a molecule is paramagnetic or diamagnetic. If unpaired electrons are present in the molecular orbital diagram, the molecule is paramagnetic, then attracted to a magnet. If no unpaired electrons are present, it's diamagnetic but not attracted to a magnet. For example, oxygen is paramagnetic because it has two unpaired electrons in its pi star antibonding orbitals. Remember, for elements up to oxygen, atomic number 8 or less, the order of orbitals is sigma 1, sigma star 1, sigma 2, sigma star 2, pi 2 px equals pi 2 py, sigma 2 pz, pi star 2 px equals pi star 2 py, sigma star 2 pz. But from fluorine onwards, the order changes. Sigma 2 pz comes before pi 2 px and pi 2 py. This small shift explains some surprising molecular properties. So far, MOT tells us 1. How molecular orbitals form, 2. How to calculate bond order, 3. How to predict magnetism, and 4. The correct order of orbital filling. With these tools, you can predict properties of diatomic molecules in seconds.